Marine power comes in many shapes and forms, and I'm now joined by Martin McAdam, who's going to tell us about the oyster, a shallow water device rather than one that relies on the tides. This one relies on the waves, and it is established, the company is established in Scotland, but he is of the Irish persuasion, and there is a connection to Belfast for this machine. Tell us about the machine. Maybe give us a little demonstration of how it works.
Yeah, indeed. I'm happy to do that. The oyster was invented by Professor Trevor Whitaker at Queen's University in Belfast, and he's Professor of Research and Development for Coastal Engineering at Queen's. And he came up with the idea of a shallow or near-shore machine. And the idea is that it's a buoyant, a very large structure which is buoyant but hinged at the bottom. So it doesn't have any mooring system. It's actually hinged directly into the seabed. And wave action actually acts on the machine, causing it to move forward and backwards. And we take this forward and backward motion and we pump using hydraulic cylinders, high pressure water. We then take that high pressure water onshore and we drive a conventional hydroelectric turbine. A lot of people will be familiar with the idea of hydroelectric turbines. They usually take their pressure from a dam in the mountains. And instead of taking our pressure from the dam in the mountains, we actually take it from the ocean of wave, the action of wave energy.
What sort of output?
Well, the output for a machine is dependent on the wave resource that's available. So if we look on the west coast of Scotland, typically the waves would be somewhere around 20 to 25 kilowatts per meter of wave crest. If we go to the west coast of Ireland, it's a little bit more, somewhere around 30 to 40 kilowatts. If we go to the west coast of the United States, up towards Alaska, we've got fantastic waves up there as well. So it very much depends on the location.
I can guess the advantages and some of the disadvantages. Tell me if I'm right. Advantage: collection of the electricity is a lot easier. It's on land.
Yeah, one of the key advantages of oyster, we say it's the 3 S's. So firstly, it's shore-based. All our electricity generation is shore-based. So you can imagine the electricity, the electric generator, the transformers, the switchgear, the converter units, all of that equipment is on the shore. And therefore, if you do have a problem, it's much easier to access it and maintain it.
And corrosion's not quite the problem it is for sunk generators.
That's correct. What we do is, that's the second S, is simplicity. What we try and put in the water is a machine which is as simple as we can make it. And therefore, again, it has very few moving parts. And if there is a problem, we hope there aren't very many problems, but there is a problem. Yes, it's more of a challenge to get offshore, and that's why all of our complex equipment is actually on land.
It would seem to me that maybe your largest problem is how do you secure it to the seabed? Do you have to have rock underlying the sand?
What we actually do is we actually put a pile into the seabed. So we actually drill into the seabed, put in a steel pile, and then fix that in place, and then we connect our machine onto the steel pile. So it's a very small footprint. It doesn't have mooring chains or anything like that.
How big is this vane or wing or whatever you call it? Yeah,
unfortunately, we haven't got a better name than a flap, so we call it a big flap. The flap
Big flap sounds unfortunate.
Well, some people suggested vane, but I don't think that makes quite sense. But the idea behind the oyster is that it captures the energy in each wave crest, if you can imagine. And therefore, the wider the machine, the better it is at capturing that energy. So we've determined from an economic perspective, a flap which is 25 meters wide is kind of the optimum size, and that would be a full-scale machine. We see that as the machine that would go into production. So that would produce about 1 megawatt of power for 25 meters of width.
That's a fair amount of power. That's the same as a fair-sized windmill.
Yes, it is.
Not the largest windmill, but a fair-sized
windmill. That's correct.
What happens with the tidal rise and fall? On the east coast here, that's fairly small. It's about a foot. But up north and in your homeland, it can be 12 feet.
Yeah.
It's very large.
We're not overly concerned about the tidal height. I mean, what we do is we design the machine. As I said, it's near shore. We like to be in about 15 meters of water depth. So we're pretty happy with a plus or minus 2 meters, in other words, 4 meters tidal range in terms of deployment of the machine. If we went into areas where you had very vast tidal ranges, some of which you're describing, then the machine wouldn't perform really very well at all.
So what is the flap made of? Is it made of steel?
Currently, we're on our
carbon fiber?
We're on our second generation machine now. We call that the Oyster 800 because that's an 800 kilowatt output machine. And that machine is actually made from steel. But we're designing our third generation machine at the moment, which we hope to deploy next year. And that will be using glass fiber reinforced plastics.
Do you have customers for this electricity up in Scotland?
Yes, we do. We have a contract with the European Marine Energy Centre, and through a utility there, they will actually purchase the power from our machine. We're also looking at a commercial project on the west coast of Scotland, and that will be fully commercial in the sense that we will be contracting directly with the utility for the power purchase.
That brings up my next question. In fact, what is the cost? What is the kilowatt cost compared to traditional sources of electricity?
I'm going to answer that question slightly differently. I would say it depends on when you ask me what is the kilowatt cost. What people care about is the cost per kilowatt hour delivered or the cost per megawatt hour delivered. That's really all that matters. And where we're at with early stage technologies, at the moment, we're about 3 to 4 times the cost of what you could achieve, let's say, with a hydroelectric scheme or with an onshore wind plant and so on. So we're more expensive. But that's typical of any early stage industry. So over the next 5 to 10 years, we see the costs coming down dramatically. And even with our third generation machine, we're going to be at half the cost of where we were with our second generation machine. So we just need to keep driving out costs from the technology. Our goal is to be at a point where we're competitive with all other renewable sources and eventually competitive with all fossil fuels.
What is your optimum water depth?
We like to be in about 15 meters. We're not, that's not an absolute. Somewhere between 12 and, let's say, 16 meters water depth. The 15-meter contour is kind of a good place for us to be.
That's very interesting. I think that's enormously exciting. Thank you very much indeed.
You're very welcome.